Very good morning. Welcome you all to the NPTEL course on electrical distribution system analysis, and today we will be focusing on field deployment of BESS. This is one of the real time experience that we have gained over last couple of years. So, we thought it will be shared among all of you. Battery energy storage system BESS are advanced solutions that store electrical energy for later use, playing a crucial role in balancing supply and demand, integrating renewable energy sources and enhancing grid reliability. They consist of batteries, power conversion systems, energy management systems and control system working together to store and dispatch energy as and when needed. BESS can vary widely in capacity, technology and application, making them versatile tool for modern power system. Today, we will conduct a field visit to explore the deployment of two different BESS on our campus. We will showcase two BESS units from different manufacturers and with varying ratings, providing a comprehensive understanding of BESS principles. At first, let us explore the single line diagram of the BESS at the Humanities, Mehta Family School of Data Science and Artificial Intelligence. Firstly, here we have two solar PV systems, one at the Hafiz Ibrahim building generating 61 kilowatt and another at the Humanities Mehta Family School for Data Science producing 35 kilowatt. Both systems are connected to their respective AC distribution boards. These AC distribution boards feed into a common ACDB which manages the power flow using different ratings of MCCBs and cables. As per the design requirements from this common ACDB, power is directed to a 75 kilowatt 150 kilowatt hour lithium ion battery. This battery operates at a 0.5 C rate, meaning it can discharge 75 kilowatt, which is half of its total capacity, that is 1 kilowatt hour in 2 hours. Essentially, the 0.5 C rate indicates that the battery charges or discharges at a rate that would fully charge or completely discharge it in 2 hours. The stored energy in the lithium ion battery is then distributed through a panel equipped with various MCCBs. This panel manages the distribution of power to different sections, one for the battery, one for the 70 kilowatt load and one for the supply from the IIT Roorkee distribution system, that is the grid. Let us now go to the field and check out this BESS system. Here we have two racks of batteries, each rack houses 10 powerful modules. Let us take a closer look at one of these modules. Inside each module you will find 3 packs and within each pack there are 8 cells, making a total of 24 cells in the module. The voltage rating of the cells ranging between 2.8 to 3.6 volt with a nominal voltage of 3.2 volt and the capacity of 100 ampere hour. At the top we have the heart of the system, the battery management system, that is BMS. The BMS is essential for monitoring and managing the health of the battery cells. It keeps track of vital parameters like voltage, temperature and state of charge, ensuring the batteries operate safely and efficiently. The BMS also balances the cells, optimizing their performance and extending the lifespan of the entire battery system. Communication protocols like CAN and RS485 are used for control with additional levels for voltage levels. The setup includes cooling fans, a green status LED and control switches for system operation. This humidity sensor features an industrial grade chip and high precision SST20 sensors, ensuring excellent reliability and accuracy. It uses an RS485 interface with lightning protection compatible with the Modus RTU protocol and support both Modbus and UART communication with an automatic reporting function for temperature and humidity data. This is a fire or smoke sensor designed to detect smoke in the air and alert you immediately. Proper installation and placement ensure these sensors effectively provide early warning, allowing you to take action and contact the fire department promptly. This is the aerosol unit designed for fire protection within battery racks. The main element is a solid aerosol compound enclosed in a metal case equipped with a cooling system and a triggering unit. Upon detecting a fire, the vent gas analyzer measures CO concentration, activating the aerosol if levels exceed the set point. This is the heating, ventilation and air conditioning, that is HVAC system. Its primary function is to regulate the temperature and airflow within the electrical panel, ensuring optimal operating conditions for all components. When the door is open, the HVAC system stops working to prevent energy loss and maintain safety. Additionally, the battery system is designed to cease operation when the door is open, further enhancing safety by reducing the risk of electrical hazards. This is the EMS, that is Energy Management System panel for the BESS. The EMS optimizes energy usage and storage within the BESS, ensuring efficient power distribution and balancing load demands. It also enhances system reliability and stability by monitoring and controlling the energy flow, ultimately maximizing the performance of the BESS. We will look into each of the components one by one from left to right. The first one is the SMPS, switched mode power supply. This device is engineered to convert an input AC voltage range of 100 to 240 at 50/60 Hz to a stable DC output of 24 volt at 10 ampere. It efficiently transforms high voltage AC power to low voltage DC power suitable for various EMS components. These are the miniature circuit breakers, MCBs, installed in the EMS panel for the BESS. Each breaker has a specific role in ensuring safe and efficient operation of the systems. MCCB 1 is used for the grid input, M2C 1 is dedicated to the auxiliary meter side, M2C 2 handles the input to the UPS, safeguarding the uninterrupted power supply, M2C 3 manages the power supply for the fan and lighting, ensuring the reliable operation, M2C 4 and M2C 5 are for the SMPS 1, covering both the AC and DC sides respectively. Below the SMPS, this is the Ethernet switch. The function of the Ethernet switch is to connect multiple network devices such as computers, printers and industrial devices, allowing them to communicate within a local area network LAN. It uses packet switching to receive, process and forward data to the destination device. To the right of the Ethernet switch is the PLC, programmable logic controller. The PLC play a crucial role in automating and controlling the various functions of the BESS. It monitors inputs and outputs, processes logic operations and ensures efficient and reliable operation of the system. The PLC helps manage the power flow, control the state of charge and discharge of batteries and integrates with other components to maintain overall system stability and performance. To the right of the PLC is the DIDO, digital input digital output device. In the EMS, the DIDO device is used for interfacing with various digital signals, enabling the system to receive and send digital inputs and outputs. This allows the EMS to monitor and control external devices such as sensors, switches and alarms, ensuring effective management of the BESS by providing real time data and control capabilities for various operational parameters. These are the fused terminal blocks within the EMS panel. The fused terminal blocks are essential for providing overcurrent protection to the electrical circuits. Each fuse within the terminal block safeguards individual circuits by breaking the connection in the event of excessive current flow, preventing damage to the components and ensuring the safety and reliability of the system. These fuse TBs also help in organized wiring and easy maintenance by clearly indicating the circuit they protect. Below the fuse terminal blocks are the regular terminal blocks. These terminal blocks are used to connect and organize multiple electrical wires within the EMS panel. They provide a secure and efficient way to manage connections between different components and systems, ensuring that electrical signals and power are properly distributed. Terminal blocks also facilitate easy maintenance and troubleshooting by keeping the wiring organized and accessible. Next to this is the water leak detector. The water leak detector system provides an effective solution for monitoring potential water leak in the server, data and computer room. This ultra compact device uses intelligent sensor capable to monitor and detect the presence of liquid. It communicates alerts via audio visual alarms to server administrators, allowing for quick response and damage control. The system's user friendly software offers technicians flexibility in navigation and managing leak efficiently, minimizing the risk of damage to critical equipment. This is another SMPS that converts 130 volt to 5 volt. It is used to step down the voltage from 130 volt to a stable 5 volt DC output, providing the necessary power for low voltage components in the system. This SMPS ensures that devices requiring 5 volt power can operate reliably within the EMS panel. To the rightmost part is the auxiliary meter. This device monitors and displays energy consumption within the EMS panel. It helps in tracking the power usage and performance of the system, providing valuable data for maintenance and operational efficiency. The meter ensures that the auxiliary systems are functioning correctly and efficiently by giving real time reading and allowing for timely intervention if necessary. To the topmost right are the plug-in relays. These relays are critical components in the EMS panel used for switching and controlling various electrical circuits within the BESS. They allow for the automation of electrical functions, enabling the system to respond to different conditions and control power flow effectively. The plug-in design facilitates easy maintenance and replacement, ensuring reliable operation and minimal downtime. These relays are crucial for the overall functionality and safety of the energy management system. In the EMS panel, the industrial PC is responsible for managing and processing data from various components of the BESS. It runs software that monitors systems performance, logs data and executes control commands. The industrial PC ensures seamless communication between the EMS and other devices, supporting real time decision making and system optimization. Its robust design is suitable for the demanding environment of an industrial setting, providing reliable operation and data processing capabilities essential for the efficient management of the BESS. Above the EMS section is the PCS, that is power conversion system section. The PCS is responsible for converting the DC power stored in the battery into AC power that can be used by the grid or the local loads. It plays a crucial role in managing the power flow, ensuring efficient energy conversion and maintaining system stability. The PCS also includes features such as grid synchronization, power factor correction and protection mechanism to ensure safe and reliable operation of the BESS. This is the HMI human machine interface screen displaying the status and performance of the BESS components. The power conversion system PCS is responsible for converting DC power from the battery to AC power for the grid or local loads. Here the PCS shows a voltage of approximately 406 volt and an active power of actually minus 0.3 kilowatt and an apparent power of 3.7 kilovolt ampere. The auxiliary section indicates the power consumption of the auxiliary system within the BESS. The displayed voltage is around 235 to 236 volt with an active power consumption of 0.3 kilowatt and an apparent power of 0.3 kilovolt ampere, signifying that the auxiliary systems are consuming a small stable amount of power to support various auxiliary functions. The battery section displays crucial parameters such as the state of charge SOC, voltage, current and power. It shows the battery SOC at 99.15%, a voltage of 801.2 volt and 0 current and power, indicating that the battery is fully charged and not currently discharging or charging. This comprehensive display allows for real time monitoring and efficient management of the BESS, ensuring optimal performance and its reliability. Next, the HMI screen display various status of BESS components, providing essential information for monitoring and control. The fire system status is indicated as normal, signifying that the fire detection and suppression system is operational and no alarms or faults are present. Both AC1 status and AC2 status are shown as off, meaning that these AC inputs are currently not active. The emergency switch status is off, indicating that the emergency shutdown switch has not been activated. The ESS status is ESS running, confirming that the energy storage system is currently operational. Further down, PCS1 status and PCS2 status are both off, suggesting that the primary and secondary power conversion system are not active at the moment. The battery mode is ideal, indicating that the batteries are neither charging nor discharging. The battery 1 status and battery 2 status are both normal, showing that the both battery units are functioning correctly without any issues. Lastly, the LR switch is set to local, meaning that the local control is enabled for the system setting and operations. If the LR switch is set to remote, it means that the system is being operated from the central EMS via cloud, allowing for centralized control and monitoring of the BESS. Now, moving to the breaker control section, this section displays the status of various MCB switches. From this screen, we can directly control the opening and closing of circuit breakers in the LT panel. For example, the BESS load grid spare and common ACDB breakers can be managed from here. Additionally, the current grid status is shown as on, indicating that the grid connection is active and operational. This interface allows for convenient and efficient management of the electrical connections and their status. The HMI includes an alarm section which is critical for monitoring the system status and ensuring its safe operation. The alarms provide real time notifications of any issues or irregularities within the BESS. These alerts can range from minor warning to critical alarms, indicating problems such as overvoltage, undervoltage, overcurrent, temperature, anomalies or communication failures. Inside the settings section of the HMI, there are several important controls for managing the BESS. The ESS switch is set to on, indicating that the energy storage system is active. Below this, there are options for active power control mode and reactive power control mode. These modes allow for precise management of the power output and reactive power compensation respectively. In the active power control mode of HMI, several modes are available for managing the BESS. These includes none for no specific control, manual mode for direct operator control, energy shift to optimize energy use by storing and realizing energy during different demand periods, and backup power to provide continuous power during grid failure and islanding operations. These operations enable flexible and efficient management of the BESS, adapting to various operational needs. The HMI screen shows setting for managing peak saving and manual mode. Peak saving includes valley filling and peak saving filling percentages set at 5.0% to 10% 0% respectively, along with a max charging power set at 0 kilowatt. These settings helps optimize energy used by charging the battery during low demand period and discharging during high demand period to reduce peak load. In manual mode, the active power command is set to -50 kilowatt, allowing direct control over the power output to manage the system's energy flow as needed. To the right is the setting for the energy shift mode, which optimizes energy usage by scheduling charging and discharging times. The charge process is set to start at 8 am with a duration of 400 minutes, and it stops when the battery reaches 100% state of charge at a power of 50 kilowatt. Discharging begins at 6 pm, running for 500 minutes until the battery SOC drops to 30%, also at a power of 50 kilowatt. These settings ensure the battery charges during off peak hours and discharge during peak demand, optimizing cost and energy efficiency. Before moving to the reactive power mode, it is essential to save any setting changes made to ensure the system operates with the latest configurations. In the reactive power control mode, you can select between manual mode and PF control mode, that is power factor control. Manual mode allows direct input of reactive power command in kVARs, giving operators precise control over reactive power settings. Now, the reactive power command is set to 0, indicating that we are not injecting or absorbing any reactive power. This is the LT low tension panel, which includes several molded case circuit breakers, that is MCCBs labeled for specific functions. BESS MCCBs for the battery energy storage system, spare MCCB for additional circuits, load MCCB for load circuits, solar MCCB for solar input, and grid MCCB for the grid connections. The panel also includes digital meters that display real time electrical parameters such as voltage, current, and energy consumption for each section. These meters provide critical information for monitoring and managing the performance and safety of the electrical system, ensuring efficient power distribution and protection of the connected circuit. The MCCBs and the meter together help maintain the system's reliability and operational efficiency. If we zoom in on one of the digital meters, for example, the one for the grid, we can see the average voltage, current, and frequency of the grid. Similarly, there are average voltage, current, and frequency readings for phase 1, phase 2, and phase 3. The meter also displays the phase to neutral average voltage, current, and frequency. The active power flow can be observed in the 3 phases, and similarly the reactive power and apparent power flows can be seen. This shows an MCCB labeled connected to the RYB phases. The MCCB featured a red off button and a black on button, allowing for manual operation of the circuit breakers. The indicator shows that the breaker is on and discharged, meaning it is currently active but ready to trip if a fault occurs. The MCCB provides essential protection by automatically disconnecting the circuit during overload or short circuiting, ensuring safety and preventing damage to the electrical system. This is a change over switch which is used to switch between the grid and the BESS. The switch allows for manual selection of the power source, ensuring that the system can either draw power from the grid or utilize stored energy from the BESS. This setup is essential for maintaining a continuous power supply, enabling seamless transitions between different power sources depending on availability and demand. This is the LT panel for the grid and the load. The changeover switch is rated as 200 ampere 415 volt AC. Here two different rooftop solar PV systems are connected. This setup harnesses solar energy to generate electricity, contributing to the building's power needs and reducing dependence on the grid. The generated solar power can be used directly or stored in the BESS for later use. Integrating solar PV system with BESS ensures efficient energy utilization and enhances the building's energy sustainability. The first system installed on the Hafiz Ibrahim building is rated at around 61 kilowatt. This is the ACDB of the solar PV for the Hafiz Ibrahim building. Here we can see that all the solar PV panels are connected in series to one another. The combined cables from these panels are then directed to the inverter of the PV system. This series connection allows the voltage of each panel to add up, optimizing the power conversion process by the inverter. The inverter then converts the DC power generated by the PV panel into AC power, which can be used by the building or stored in the battery energy storage system. The Solivia 30 inverter is designed for solar PV systems supporting a DC operating voltage range of 200 to 1000 volt with an MPP range of 480 to 800 volt. It can handle a maximum DC input voltage of 1000 volt and a maximum operating current of 68 ampere. With 34 amperes per string, one of the AC side it outputs a nominal voltage of 3 phase /N/P at 230/400 volt and operates at a frequency of 50 or 60 hertz. The inverter can continuously output 46 ampere of current, delivering a maximum continuous power of 30,000 volt ampere. This shows the display of the solar inverter providing real time performance matrices. The E today value indicates the energy generated today, which is 58 kilowatt hour. The run time shows the system has been operating for 10.9 hours. The power reading shows the current power output, which is 2163 watt. The display also features a graph illustrating the power output trend over the day, enabling monitoring of the solar PV system's performance and efficiency. These matrices are essential for assessing the system's productivity and ensuring it operates optimally. This is the solar series connection for the second solar PV system, which is near Mehta school and rated around 35 kilowatt. The combiner box aggregates the output of multiple solar panels, combining their currents into a single output. The individual cable from the solar panel enter the box where the electrical connections are consolidated. This setup simplifies the wiring and provides a central point for monitoring and protection, ensuring efficient management and safety of the solar PV system. Similarly, this is the inverter for the Mehta school solar PV system. Here the two solar PV are coming through the cable to combine in a common ACDB. This is the common ACDB for the solar PV system. The ACDB is a crucial component that houses the protection devices and control mechanisms for the solar PV systems. It contains 3 circuit breakers, each connected to different phases red, yellow and blue of the system, ensuring proper distribution and safety. The ACDB consolidates the AC output from various inverters and direct it to the grid or other loads. This setup helps in managing and protecting the electrical distribution, ensuring efficient and safe operation of the solar PV system. The LT panel for the grid is present besides the solar ACDB. The grid is required for the solar ACDB to start the inverter by providing a stable reference voltage and frequency for synchronization. This ensures safe and efficient operation of the solar PV system, aligning its output with the utility grid. This showcases the load LT panel for the Mehta school department. The panel is divided into sections with various components for managing and distributing electrical power to different loads. On the top left, there are meters indicating important electrical parameters such as voltage, current and power factor. The middle section houses multiple circuit breakers, each corresponding to different load connections, ensuring safe and efficient distribution of electricity. The right side of the panel features indicators lights for each phase, red for L1, yellow for L2 and blue for L3, providing a visual status of the electrical phases. If we zoom into the meters, it shows the current in amperes 211 amperes, the voltage in volts 422 volts and the power factor 0.915 across 3 phases L1, L2, L3. These values are crucial for ensuring that the loads operate within safe and efficient parameters, helping to prevent overloads and maintain system stability. We have already seen how the local EMS functions. Now, let us look at the central EMS. The ELINA server functions as the central energy management system via a cloud based software platform designed to remotely monitor, analyze and control all your distributed energy resources DRs. ELINA server provides comprehensive analysis of individual and aggregated site performance matrices, monitors battery health and performances and tracks predicted battery lifetime and warranty terms. This platform can be accessed through a web based user interface or integrated into existing web based software using APIs. The system can be hosted on the cloud or on premise server tailored to your specific needs. This web page provides a real time monitoring and control interface for the battery energy storage systems BESS at IIT Roorkee. The dashboard displays key matrices including a power capacity of 75 kilovolt ampere and an energy capacity of 153.6 kilowatt hour. It shows the current site Roorkee where the BESS is operating in energy shift mode with real time power output that changes dynamically. The map pinpoints the BESS location at Roorkee. This interface allows users to efficiently monitor the system's performance and status. In this section of the interface, the graph displayed provides a comprehensive view of the system's performance over the selected time period. The x axis represents the days of the month, allowing you to observe trends and variations over time. The graph uses a dual y axis to illustrate two critical parameters. The left y axis in kilowatt shows the active power of the energy storage system indicated by the green line, while the right y axis in percentage represent the state of charge, that is SOC of the ESS, depicted by the orange line. This dual representation enables you to easily correlate the active power fluctuations with the charging and discharging cycle of the ESS. Additionally, on the rightmost side of the screen, a series of scrolling matrices provides detailed real time data about various aspects of the microgrid. These matrices include the operational status of the ESS switch, the active and reactive power modes, the current ESS active and reactive power outputs, the SOCs, the power generated by the photovoltaic systems, the power exchange with the grid, the active power from the diesel generators, the load's active power demand and the auxiliary active power consumption. This detailed information is crucial for monitoring the microgrid's performance and making informed decisions based on the latest data. You can click on the graph icon to see the graph for that specific metric. For example, checking the graph for PV power, this is the graph for the PV power. The other pages includes the event section which displays warning and alarms. In the battery section, you can check matrices such as battery module voltages, temperature, current and other relevant data. Finally, in the mode section, you can select the operating mode for the battery energy storage systems similar to the option available on the HMI screen, but with the added capability to perform or change settings remotely. These data and information are essential for research purposes. There are many more features and details to explore in this interface, but due to time constraints we will limit our discussion to this overview. Before we move to the second BESS located at the electrical engineering department, let us review the microgrid setup at this department. The department has a total load of 111 kilowatt supported by a 170 kilowatt power rooftop solar PV system and a 200 kilowatt hour lithium ion battery. The microgrid also includes a diesel generator for backup and a utility connection that can function in both grid connected and off grid modes. This integration of renewable energy, energy storage and traditional power generation ensures a reliable and sustainable power supply. Now, let us move to the field where the BESS of electrical engineering department is connected. Here is the nameplate of the lithium ion battery system. The specifications indicate it is rated at 200 kilowatt with the rated AC current of 450 ampere and a rated AC voltage of 375 volt. Operating at 50 hertz, the battery has a capacity of 205.5 kilowatt hour and a rated DC voltage of 729 volt, operating at a 1C rating, meaning it can discharge its full capacity in about 1 hour. This is the entire battery unit consisting of several battery units stacked together. There are 7 racks connected in series and parallel, achieving a total energy capacity of 205.5 kilowatt hour. Next is the battery management system BMS of this battery rack, showcasing essential components and connections. The BMS includes clearly labeled B minus and B plus terminal for battery connections, an auxiliary power in, that is AUX PWR in for auxiliary power, and various status indicators such as COMM, alarm, run, current and fault. These indicators provide real time information on communication, operation and any system fault. Additionally, the system has communication lines labeled as rack COM and cable COM, essential for data exchange between the battery systems. Now, let us go into the PCS and EMS section of this BMS, which is situated at the back of the battery section. Let us now check the PCS section of the BESS. These are the internal components of the energy storage converter with 3 power conversion modules labeled 1, 2 and 3 displaying operational status. These modules are critical for converting stored DC energy from the battery system to AC energy for grid integration or other applications. The setup indicates a robust design aimed at high efficiency and reliable performance in energy storage applications. These are the specifications for this PCS. The AC port specifications includes a rated AC voltage of 480 volt with plus or minus 10%, an AC frequency of 50 hertz or 60 hertz with a plus or minus of 5%, an AC current of 360 ampere and a rated power of 299 kilowatt. The DC port specification feature a voltage range of 250 volt to 820 volt DC with a rated DC current of 498 ampere. This is the control panel of the BESS. The panel includes an upper section housing a user interface with a display which provides real time monitoring and control options for the energy storage systems. Now, let us look at the 5 kVA uninterruptible power supply UPS. This UPS provides continuous power during outages or fluctuations, ensuring stable power for the internal controls of the BESS. Next, we have the isolation transformer. The nameplate of this ABB cast resin dry isolation transformer shows it operates at 50 hertz with a capacity of 250 kilovolt ampere and has a rated high voltage of 433 volt and low voltage of 400 volt. The rated currents are 333.3 ampere high voltage and 360.8 ampere low voltage. The transformer has a YND11 vector connection, an insulation class of F and an IP45 enclosure rating. Here is the control panel for the isolation transformer. It monitors critical parameters such as temperature and fault conditions and features indicators for faults, high temperature, high voltage and fan status. These are a series of LT panels in a microgrid setup. The leftmost panel receives grid power from the substation. Subsequent panels represent various control functions for the microgrid, including controls for the battery energy storage system, that is BESS, solar integration, grid connection and load management. These LT panels are essential for managing and distributing power efficiently within the microgrid, ensuring reliable operation and integration of different power sources and storage systems. This is the interior of the LT panel within the microgrid setup. These panels house various control and protection equipment essential for managing the power distribution. Each panel includes switches, circuit breakers and status indicators. The circuit breaker ensures safety by protecting the system from overloads and short circuits, while the status indicators provides real time information on the system's operational status. Additionally, there are warning signs indicating high voltage, emphasizing the need for safety precautions. These LT panels play a critical role in the efficient and safe distribution of power within the microgrids, integrating various power sources and managing the load effectively. This is the SCADA system interface for the BESS or central EMS at IIT Roorkee 220 kilowatt microgrid. The interface provides a detailed schematic of the power flow and system components. It shows the grid connection point where the microgrid interfaces with the main power grid and includes a 415/400 volt 280 kilovolt ampere isolation transformer specifically for the BESS. Additionally, the interface highlights 170 kilowatt power rooftop solar PV system and its inverter. Various QA panel QA201 to QA204 represent different circuit breakers and their operational status within the system. The schematic also indicates the power distribution to the load and a spare circuit for the future use. This is the status of the rooftop solar PV system on the SCADA system interface. The PV system is connected through QA203 with the inverter status. The current measurement for each phase are also given here. The active power P act generated by the PV system is 44.75 kilowatt with a reactive power Q act of minus 28.67 kVAR, resulting in a power factor of minus 0.86. The operational status indicates the PV system is online and healthy. This displays the status of the 200 kilowatt hour lithium ion battery currently at 0% charge. This is the circuit breaker connected via a 415 volt/400 volt 280 kilovolt ampere isolation transformer. The interface is in operator mode, including detailed operational parameters with controls for power set points and various monitoring matrices, ensuring efficient energy management and grid stability. This is the status and control interface of the grid. The interface displays various operational parameters, including the real time status of the grid connection, microgrid status, online, islanded or connected, and alarms which are critical, non-critical or warning. It also provides detailed power matrices such as active power, reactive power and power factor. The SCADA CMS interface for IIT Roorkee BESS provides real time monitoring and control of the microgrid, including grid connection, battery status and PV system integration. It displays detailed operational parameters such as voltage, current, power and system health status, ensuring efficient energy management. The system support automatic and manual mode, facilitating reliable and stable operation of the microgrid. As we wrap up the discussion on the deployment of battery energy storage system BESS, we have explored various devices within BESS and the different aspects of their operation. I hope this discussion has provided you with a comprehensive understanding of BESS and its significance in modern power systems. To conclude, I wish to express my gratitude to the Electrical Engineering Department and the Institute Works Department of IIT Roorkee. I am also immensely thankful for the support and collaboration from Ampere Hour, Tata Power, Delta Electronics, ABB, Hitachi, as well as admired lab of IIT Roorkee. With the support, the lab has been developed with all the cooperations received from my research scholars. Special thanks go to all the professors, engineers, staffs and students, especially the research scholar, whose dedication and effort have made this achievement possible. Special thanks to Sobik for wonderful contribution and Pankaj for coordinating the whole event. Thank you.